Doc here with Chapter K, Spherical Mirrors, Light and Visual Phenomena. Here we're going to look at the I-arc model, which states here I have a question, an inquiry, and in this case it's going to be to find an image for a curved mirror. A stands for apply. I will apply my rules to locate the image. 3, I will reflect on my analysis to see if there's an observation that supports it, because good science requires observation and analysis. And 4th, I will communicate my answer C by giving the diagram and image characteristics. Well, for a curved mirror, we have a center of curvature. If you take this part of a circle and complete it, you would get the center of curvature here. We have a point O called the origin, which is the intersection of the optic axis, a reference axis, and our mirror. This is a convex mirror, by the way, since the light's coming from the left side, and that's a convex surface from that point of view. And F, called the focal point, is the point between O and C, the midpoint. Now we have 3 neat rules that we can use. Ray 1 is parallel to the axis, and that will reflect as if coming from F, the focal point. Ray 2 is aimed at C, the center of curvature, and it bounces right back. And if you extend the dotted lines behind the mirror, you see they cross at this point, which is the image of the top of the arrow. So we have here then a nice small image. Now, if we want to reflect on this by looking for an observation, we need look no further than the Escher, beautiful work of Escher, where you see the images are smaller. And here, if you touch the mirror, the image is actually the same size, and you get farther and farther away from the mirror, they get smaller and smaller, which is something that you can verify by drawing this arrow at different places. So that is very, very nice. And here, these kind of mirrors are sometimes used for surveillance, where you can get a wide angle of view. Let's look at some other examples. Here, for example, in a car, you can see a lot with a convex mirror. And there's one from my car, which I actually broke trying to get back out of my garage. Not too smart. Be careful when you back out that doesn't happen to you. And here's again the example of a convex mirror to get a wide angle of view on the road. And this is the surveillance case in the store where the cashier could see like everybody in the store easily, or practically everybody in the store. We put these at the right places. Here is a motel where you can see around the corner, see who's coming. And this is an astronaut, convex surface, showing a similar effect, wide angle of view. And here's a student Avi, sunglasses, convex. I stop him. And here, Avi, you can see the image of the photographer. That's me, down there on one knee, taking a picture. And that's a smaller image that you see there. Very nice. Here's a small image of my son with a convex balloon and a Christmas bulb. This was published in our school paper many years ago by one of my students. Very nice. So if we come back to, let's go back to the notes and let's look at another case. Before we do that, the image characteristics are light doesn't really go there, so that's a virtual image, it's smaller, and it's upright. And that's the communication with the diagram, and we got all 4 aspects done. Let's do another one, but before we do that, I want to mention that you have another trick here, ray 3. If the light ray should go toward F, it goes out parallel. It's ray 1 backwards, and sometimes we might use that. See, if I started here and aimed at F, if I aimed at F, I would have to aim a little lower than that ray, see, to aim at F. And if I went out parallel, that would appear to come from the same top there. But we only need 2 rays to locate the image. So let's look at another kind of a mirror here. And this is one where we flip the mirror and use the other side. That's called a concave surface from the perspective of light on the left side. And here's my object arrow. And the question is, where is the image? All right, that's the inquiry. And the first step is to apply rules. Now, the rules here are pretty much the similar that you have for the convex case. Parallel ray. Here I can actually go through F because when I reflect, F is on the left-hand side. See, if I have the circle here, C is on the left, and F is halfway between C and O. So this one goes through F, ray 1. Ray 2, before I aimed at C, well, I can still aim at C and actually go through C, and I bounce right back. The two rays cross here. Light really goes there, so that's a real image, and it's smaller. Ray 3 was not needed, but ray 3 is running ray 1 backwards. If you go through F, you go out parallel, and if we do that from the top here, we would go through F like this, and then hit the mirror and go out parallel, and once again, you would agree, an observer here looking back, that the ray came from the tip there. This is an example of a real image in a reflecting telescope, and we can look here at another observation. There's my sun, and he is upside down and smaller. That's neat. And here is a picture I took of myself with a concave mirror, and I am smaller and upside down. Very nice. So that's our reflection, that we are doing good physics. And finally, the communication, the image characteristics, real image, give the diagram, and we write down real image, smaller, and inverted. Let's look at the richness of the concave mirror by considering another position where the object is now between F and O. Ray 1, parallel to the axis, through F. Ray 2, I aim so that I line up my ruler so that the tip and C are lined up, and then this hits the mirror and comes right back. And these observers conclude that the image is behind the mirror. We need to use dotted lines, and that's a signal that it is a virtual image. And the image here is larger, and we look for an observation of that effect. And you might be familiar with the makeup mirror, where if you have a makeup mirror, you will look larger. Let's see, like this, for example, there. See, that's the concave mirror, in contrast to the convex, where the face is smaller. So here is a picture I holding a mirror here. This is a convex mirror, and this is the concave, see, which gives me the larger face. On the left, I have the convex mirror, which gives me the smaller image. That's neat. See, the makeup mirrors. All right, so that's cool there. So we can then conclude with our communication phase that we have a virtual image. It's larger and it's upright. Anamorphic art is neat, where sometimes they use distorted images with mirrors to render them correctly. I want to show you an example of that with anamorphic art, where here you have a distorted image of a person, but when you put the cylinder here, the cylindrical mirror, you get an image of the person looking correctly. Very, very nice, like see here. Very nice. The image is all smeared out there, but with the reflection, things look nice, look corrected. You don't have to have a mirror for some of these. Some of these are different point of view of observing. This is the Holbein, where if you look from the right angle, this smeared image here looks like a skull. Here's another example where if you look from the side, this image looks then with correct perspective. William Cochran here, a contemporary artist, does a beautiful job of this in Maryland, where he here sketches, draws, paints on a bridge structure, an image of an archangel, where if you look at the right from the right angle, perspective from the as you're walking up above, looking at the bridge, you see a beautiful work come into nice sharp image. Very nice work by William Cochran. That's anamorphic art. Here's another example with a concave mirror, a trick used at the University of Maryland, where they had a bulb, a real bulb, upside down, and ray 1 parallel to the axis goes through F. And here ray 3 is very nice to use. Ray 3 goes through F and goes out parallel, and you can see then the bulb is flipped, the image is flipped, same size, and they had a bulb they screwed in at the top. The real bulb is underneath here. That's the image of the bulb. And the professor would touch the bulb, not get burnt, and then unscrew it and walk away with the bulb, and the bulb would still be there because it's the real image you're looking at. Very nice. Here's another example of a similar idea. This commercial trick called Mirage, although it's not a mirage. You basically put a penny or a piece of candy down here at the focal point of the top mirror, so when the light hits the mirror, it goes out parallel, and then it reflects to go to the focal point of the bottom mirror, and these observers see a piece of candy here or a penny, but they cannot touch it. Their hand goes right through it because it's not a physical object that's there. It's an image. These laws that we're giving you follow the laws of reflection, but the laws of reflection are too detailed to use when you look at these problems. If I go parallel to the axis and drew my normal in from C, that's the normal, the angle of incidence would be equal to the angle of reflection, but we'd rather just use the rule, the quick rule, parallel through F, and we're done. But I wanted to show you that these rules are based on what we know, the law of reflection, when you apply the normal and look at the angles of incidence and reflection. The ray that goes through the center is along the normal, so it bounces right back, see? And this ray 3, that would be ray 1 backwards, all of these obey the law of reflection. We might here look at a neat application with the satellite dish, which is concave, and the rays from the satellite come in parallel and go to the focal point, and there you put a detector that then goes to your TV so you can see satellite TV. Of course, here was on TV, local station. At one point, I'm holding a concave mirror here, and you might be able to see faintly here the chairs in the auditorium inverted, upside down. The small chair is inverted, and you are here on the observer side of the mirror, which would be to the left, but the images are tiny, and they're between F and C. That's very, very interesting to note that. So if we were here to go back to this analysis, what we're saying is that the chairs are out here, but the chairs have an image that are upside down, and they're between C and F. So I'm holding the mirror here, and the chairs are right there, see, in that little region there. Depending on where they are here, they're between C and F. Very, very nice application there. How do you measure focal length? Well, you can measure focal length by measuring the distance from F to the mirror. We like to use uppercase for the point and lowercase f for the distance that is the focal length. So the distance from big F to the mirror is little f, the focal length. And you can measure that using rays from the sun, although I don't recommend that because the light's very bright. You can cause a fire. You can look at something that's too bright for your eyes. You don't want to do that. A better way to measure the focal length of a concave mirror would be to set up the position where the object is the same size. That's going to be at point C, and that's twice the focal length, because from O to F is the focal length, and there's this F plus F. Then you just divide by 2. That's a safer way to do that. Very, very nice concept, the focal length. So here, if we look at the bottom here, the last comment I wanted to make is that capital F is the focal point itself, and little f is the distance from the focal point to the mirror, the length itself. That's convention we use. Well, I hope you enjoyed the review, and see you next time.